This one index structure is why vector search can be fast at scale. Build it end to end. By the end, you will understand how to build a fast similarity index, query it, and add a simple re-rank step to improve accuracy. I'm Professor Pi, teaching AI foundations with simple Python. Think about a recommendation pipeline or a semantic search. You have a lot of embeddings and you need nearest neighbors in milliseconds. Brute force scanning every vector is exact but slow as your data grows. HNSW is an index structure people reach for when they need very fast approximate nearest neighbor search with high recall. It is a practical middle ground between full exact search and cheaper, lower quality hashing methods. At a high level, HNSW arranges items into a multi-level graph that guides a greedy search toward close vectors quickly. Imagine a city map with local streets and a few highways. You hop between highways to get close, then walk local streets to the exact house. That intuition explains why searches touch only a tiny fraction of the collection, yet still find very similar items. We will build a tiny HNSW index with hnswlib and NumPy. Add vectors, query it, check the approximate answer against an exact cosine calculation, run batch queries, and finally do a candidate re-rank. This keeps the code small and the ideas clear before you scale up. First, we will create a tiny index and run a single lookup. This snippet creates a tiny HNSW graph using hnswlib and performs a single nearest neighbor lookup. The index object configures a cosine space with 2 dimensions, which is ideal for similarity of small vectors. The call to initIndex allocates capacity, and add items inserts 3 float32 vectors with labels 0 through 2. The function knquery then searches the graph for the closest vector to the query vector, 0.95, 0.2, returning labels and cosine distances. We convert distance to similarity as 1 minus the distance to make it intuitive for human interpretation. The printed best ID and sim show the nearest label and its similarity, confirming the index is working and gives a sensible top hint. Next, we append more items and request multiple neighbors. This example expands the same HNSWlib index by adding 2 more vectors in a single add items call. Batch inserts are faster than many tiny calls, and labels 3 and 4 are appended to the existing graph. We then query with knquery at k equals 3 to retrieve the 3 nearest labels to the vector, 0.9, 0.2. The variables L and D hold label results and distances respectively. Converting the label row to a list gives a clean, readable ranking. A higher K returns deeper neighborhoods, which is useful for downstream steps like re-ranking. The printed K3 IDs shows the ranked neighbors for the query, which confirms multi-result retrieval and that neighbors are ordered by increasing distance. Now, we will compare the approximate neighbor against an exact cosine search. This code sanity checks the HNSWlib result by comparing it with an exact cosine search. The variable q is the query vector. Using getCurrentCount and getItems, we pull all stored vectors A back from the index to reconstruct the small corpus. We compute exact cosine similarity with NumPy by taking the row-wise dot with q and dividing by the product of L2 norms, which yields true cosine scores. The variable exact holds the best label by exact math, and approx comes from knquery at k equals 1. If you ever see a mismatch, raising EF later can improve recall at the cost of latency. The printed match and exact ID confirm whether the approximate result equals the true best and helps you trust the index. Then, we will exercise the batch query API to show throughput benefits. This snippet demonstrates batch querying in HNSWlib to increase throughput. The variable q contains 3 query vectors, each of the same dimensionality as the index. Calling knn query with the entire batch returns labels and distances for all queries in one go, reducing Python overhead and improving efficiency. We flatten the labels, so the top one for each query becomes a simple list, which is easy to inspect or log. For larger workloads, batching can dramatically cut per query latency and raise overall requests per second. The printed batch top one shows the nearest neighbor label for each query in order, confirming the batch API is functioning. Finally, we will increase search effort and re-rank candidates exactly for better accuracy. This example builds a practical baseline. Use HNSWlib to fetch candidates quickly. Then re-rank exactly. We first set EF to 64 with setEF, which increases search effort to boost recall. The call to knn query at k equals 5 returns candidate labels and distances. We retrieve candidate vector C with getItems and compute exact cosine similarity in NumPy by normalizing with L2 norms and scoring each candidate. The index J identifies the best candidate after exact scoring, and we map that back to the original label. Increasing EF generally raises accuracy, but also latency. Decreasing it does the opposite. The printed re-rank ID and sim show the final, improved best match after exact re-ranking. Putting this tiny example into a real project is straightforward. Replace the 3 to 5 toy vectors with thousands or millions of embeddings. Keep batching for queries. Use the candidate re-rank step when exact quality matters. For example, in a search results page or a recommendation feed. Tune F for your latency versus recall budget and monitor end-to-end timings. Recap what it is. HNSW is a multi-level graph index that finds nearest neighbors fast with greedy search. When to use it? When you need low latency, high recall similarity search over large embedding sets. One caveat, it is approximate, so you may need to tune EF and optionally re-rank candidates for perfect accuracy. Next step, tune EF and measure trade-offs by sweeping EF values and recording latency and recall on a validation set. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.